Hi 213. In this video we're going to talk about section 11.4 where we work with angles some more. So we're going to begin with discussing vertical angles. Vertical angles are created by intersecting lines and they are a pair of angles whose sides are two pairs of opposite rays. So let's see exactly what this looks like. Okay, so here we have intersecting lines, and the angles that we call vertical angles are a pair of angles whose sides are two pairs of opposite rays. So to use the labeling system that's here in this example, we call angles 1 and 3 vertical angles. 1 and 3 vertical angles. They're sort of opposite of each other, right? Notice how these are angles whose sides are two pairs of opposite rays, right? So the rays are going in opposite directions. And we also say, by the way, that angles 2 and 4 are called vertical angles as well. And we'll make use of this idea of vertical angles more when we talk about other kinds of angles. So specifically, I'd like to reference you to a table in your textbook, table 1112, and I have the digital or ebook copy of our textbook here, so we can look through it together, but you're welcome to open your book to page 681 to check out this table as well. So let's talk about a couple kinds of angles specifically. Supplementary angles are two angles, the sum of whose measures is 180 degrees. Each angle, we say, is a supplement to the other. What's interesting about this is that supplementary angles do not need to be adjacent to each other. They don't need to share a side. So you can have supplementary angles like these two angles. Notice they are not adjacent to each other. They do not share a common vertex and common side, but they are supplementary to each other because their angle measures add to 180 degrees. Right? This is an example of supplementary angles that are adjacent to one another. And in general, if we don't know a specific number for one angle, for example, this one is just labeled as x, we don't know what the actual number is, then we know because these two are supplementary angles that this one has to be 180 minus whatever this is, right? So notice that when you add these two angle measures together, you just get 180, right? So if this is x, this has to be 180 minus whatever this is, right? Alternatively, we have what are called complementary angles. These are two angles, the sum of whose measures is 90 degrees. Each angle is a complement of the other, right? And again, complementary angles don't have to be adjacent. They don't have to share a vertex and a side. So here we have these two angles of 60 and 30, which would be considered complementary because they, when added together, equal 90 degrees. These are an example of two complementary angles that are actually adjacent to one another. And notice that the notation here shows that when these two are added together, they create a 90-degree angle, a right angle, yes? And again, just like with the supplementary, if we don't know specifically a number for one of them and we just want to label it x, then we know if this is x, this angle here has to be 90 minus whatever that is, because when you add these two together, you want to get 90 degrees if they are complementary. Okay, let's go to the next page because the table continues to the next page of our textbook on page 682. So here we see a little bit, something a little bit different, right? We're now actually looking at what's called two pairs of or a pair of lines here, two lines. They may intersect somewhere, they may not, we don't know. And this is called a transversal, right? So here we have two lines and what is being cut by a transversal, okay? We can call interior angles the angles that are between the two lines cut by the transversal. So here we label the angles as 3, 4, 5, and 6 as being the interior angles, the angles that are sort of on the insides of the two lines that are being cut by the transversal. The exterior angles then are the ones not between the two lines cut by the transversal. So angles 1, 2, 7, and 8 would be exterior on the outsides of the two lines. Alternate interior angles are those that are between the two lines cut by the transversal and on opposite sides of the transversal. So here they have to be between the two lines, so on the insides they have to be interior angles, but they have to be on opposite sides of the transversal. So 3 and 6 are alternate interior angles, and 4 and 5 are alternate interior angles. Alternatively, alternate exterior angles, well, let's think about that for a second. Exterior angles are ones that are on the outsides, right, 1, 2, 7, and 8, but they need to be alternate, so on opposite sides of the transversal. So here we have 1, 8, or 2, 7. Those are both pairs of alternate exterior angles. Lastly, corresponding angles. These are in the same relative position when the two lines are cut by a transversal. Okay, so what that means is they sort of have the same orientation to the transversal for each of the two lines that are cut by the transversal. So angles 2 and 6, or 1 and 5, or 3 and 7, or 4 and 8. So relative to the transversal, 2 and 6 kind of have the same position, right? They're both sort of top right, yes, upright with respect to the transversal in that single line, right? Sort of top right corner would describe 2 and 6, yes, for the transversal in that single line in each situation. Okay, so this gives us some more vocabulary to work with when we're talking about angles here. Let's skip back over to our PowerPoint here. Okay, so we were working with vertical angles, and we now can move on to say vertical angles are congruent, right? So, and the reason for that is because here we have angle 1 and angle 2 making a straight line, a straight angle, but 2 and 3 also make a straight angle, which means that 1 and 3 have to be the same angle measure since 2 is itself in both of those situations. So let's skip to slide 7 because we did all of this in the tables. So this is slide 7, and we're able to make a claim here if we know that a transversal is cutting parallel lines. Okay, this is called the angles and parallel lines property. If any two distinct coplanar lines are cut by a transversal, so we've got two lines cut by a transversal, just like in table 11-12, right? If these two distinct coplanar lines are cut by a transversal, then a pair of corresponding angles, alternate interior angles, or alternate exterior angles will be congruent if and only if the lines are parallel. Okay, and let's see, I'll just make you a little sketch here, right? So if we have two parallel lines, pretend those are parallel, and I have a transversal, right? Then what we're able to say is that corresponding angles, like these here, those are going to be congruent. We could also say that alternate interior angles would be congruent. So this is an alternate interior angle with this one, right? Those would be congruent. We know actually this angle here, and this one are congruent because they are vertical angles, right? And we just talked about that a second ago. So here, this angle and this one are congruent because they are corresponding. These two are congruent because they are vertical angles. These two are congruent because they are alternate interior angles. We can also say alternate exterior angles will be congruent. So if we start with this one up here, what is going to be the alternate exterior angle of that one? It would be this one here, right? It's an exterior and it's on the other side of the transversal. Okay, and if you look at this, it sort of gives you a little stepping kind of action right here. We know this one is congruent to this one because it's alternate exterior, but we know this is congruent to this because of being vertical angles, and this one is congruent to this for alternate interior, and you can keep going, right? And this one is congruent to this one because it's a corresponding angle. Okay, so there's lots of relationships for congruence when we know that these two lines here are parallel, right? So that's a big, big, big requirement, right? So we have to have that part being lines are parallel in order to make any of those conclusions I just said a second ago. Okay, so let's think about how we can actually construct parallel lines. So if we had this line AB here, right? If we had line AB and we wanted to construct a line parallel to it, well, what we could do is locate a point C somewhere out here, right? And make this triangle ABC, right? If we make that triangle ABC, then what we can do is say, okay, take a ruler and line it up with this side AC. Okay, if you had designed this well enough so that you have a triangle ABC here and you're allowed to move it, then you can create a line parallel to line M here by just taking this blue triangle and sliding it up the ruler, right, like is shown in this figure over here. If you slide it up the ruler, always maintaining that AC is on that ruler and the ruler does not move, then the new resulting top of where this triangle is, where AB ends up, right, that will be parallel to the original line M that you started with. Okay, so this is sort of a basic, like, rudimentary construction of a parallel line. So let's talk about angles inside of a triangle now. So I think we all probably have heard that the sum of the measures of the interior angle, sum of the measures of the interior angles of a triangle is 180 degrees. What this means is if you take angle 1, angle 2, and angle 3, and you take their measures and you add them up, you're going to get 180 degrees. Well, why is that true? Let's see if we can prove it to ourselves here. So if I take this triangle ABC and I draw a parallel line L to line M, notice we just talked about how to do that, right? Yes. So if we wanted to do that, for example, we would have to do what? Place a ruler, for example, maybe along this side here, right? And then what we could do is slide this whole triangle up. Right? We could slide it up, and where it now results, where if we slide it high enough so that our side here, our side AC ends up at point B here, we would have sort of a triangle that looked like this, right? Kind of like that, living up there like that. Okay, where that triangle ends up, that horizontal line right there is going to be parallel to AC, right? Or what they call line M. Okay, and that's where this line L is being generated from, right? It would be the terminal or lining up with this side of this triangle here, okay? And that's why we talked about constructing a parallel line in the first place, right, in the previous slide, okay? So that line L can be constructed based on having this triangle and sliding it up. And then what we can do is use this idea of alternate interior angles to prove then that adding up angles 1, 2, and 3 will be 180 degrees. Okay, so notice that when this line L is parallel to M, what I have is that this angle here at this one is the same or congruent to this angle here, because those would be alternate interior angles, right? AB would be considered to be the transversal here, right? That's the transversal. Angle 1 is congruent to this angle here at 1, okay? Also, if I consider the transversal to be this piece here, I know that angle 3 here is the same as this angle right here. That's why that's labeled 3. All right, and angle 2 remains the same. Well, because angles 1, 2, and 3 when added together make a straight line, yes, that is a straight angle, that means that angle 1 plus angle 2 plus angle 3 equals 180 degrees. And then we've proven that angle 1 plus angle 2 plus angle 3 will equal 180 degrees when added together. Okay, let's try an example. So in the framework for a tire jack, ABCD is a parallelogram. ABCD is a parallelogram. If angle ADC is 50 degrees, measured here, what are the measures of the other angles in the parallelogram? Okay, so let's make use of our ideas of alternate interior angles, maybe at corresponding angles, that kind of a thing. So notice that in parallelogram, we know that these opposite sides here are parallel. Yes, so what that means here is that if we consider these first two like this, right, that means we've got parallel lines with a transversal. Yes, okay, that's a transversal, which means that this angle of 50 degrees right here means that this angle 4 is also 50 degrees. Right, because those are corresponding angles, which means that what? Angle 4 and angle 1 make a straight angle here, which means angle 1 has to be 130 degrees. Okay. Also, since we know angle 4 here is 50 degrees, we can say this is a parallel line, this AD is parallel to BC, right? And AB would be the transversal. So that means that angle 4 is the same as angle 2 because those are alternate interior angles. So that means that one has to be 50 degrees. Okay? And finally, we can sort of use a little bit more reasoning here that if this angle 2 is 50 degrees here, that's the same as this angle here because AB is parallel to CD and CB would be a transversal, right? So this one has to be 50 degrees, which means that angle 3 and that angle are supplementary. We can use those words. So that means that this one has to be 130 degrees. Okay? And let's see if we're right. Measure of angle 1 is 130 degrees, 2 is 50 degrees, and 3 is also 130 degrees. Excellent. All right, so let's try this example. In the figure, we know M is parallel to N, so again, you can make some notations here if you like to denote that we have parallel lines. K is a transversal, so K is a transversal cutting those two parallel lines. Okay, so explain why the measure of angle 1 plus the measure of angle 2 has to be 180 degrees. Well, we just saw this right here in our picture. Notice that these sort of interior same side of the transversal angles here, the 50 and the 130, those both add to 180 in both situations, right? Let's see if we can explain why it's true in general, right? So what we can do is say that angle 1 here is an alternate interior angle with this angle here, right? Yes? And since that angle and this angle 2 are supplementary, then that means that angle 1 plus angle 2 must equal 180 degrees, right? That's one way to describe it. What we also can do is say angle 1 and angle 3 are corresponding angles, so in case instead of doing alternate interior, we can use corresponding, right? Angle 1 and angle 3 are corresponding angles, so 1 and 3 have to be equal. And angle 2 and 3 are supplementary. Angle 2 and angle 3 are supplementary, so we know they have to equal 180. So then we say, well, since 1 and 3 are equal, I can substitute then. So 1 and 3 are equal, which means the measure of angle 1 plus the measure of angle 2 is 180 degrees. So that's just an alternate argument for proving that, right? So what that means is that these two angles that are on the same side interior of a transversal, when you have parallel lines, those add to 180 degrees. So let's now think about if we are working with a convex polygon. Remember, that means it doesn't have any sort of indentations, right? And its sides are straight. When we talk about the sum of the measures of the interior angles of a convex polygon with n sides, we know that the sum of the measures has to be equal to n minus 2 times 180. Okay, and we can prove that in a variety of ways. We won't prove it in the video right now because it might take a little bit too much time for our video that's already getting a little bit too long, right? I'm already starting to lose you, but we're almost right at the end. If instead we wanted to talk about the measure of a single interior angle of this regular n-gon, right, this regular n polygon, if this is the sum of all of them, then to get the measure of just a single one, all we have to do is take this value here and divide by the number of sides, divide by n. That'll give us the measure of a single interior angle. Okay. Also, what we can do is talk about the exterior angles. Remember, exterior angles are just the measures of the angles created when you continue the side out, right, in a direction like that. So these are all exterior angles. There are other exterior angles, but we want to talk about just moving all these sides out in a single direction. We don't want to go this way too, right? We don't want to do that. We just want to go in one direction, okay? So here, if we talk about the sum of the measures of the exterior angles, mainly we're talking about if you do B1 plus B2 plus B3 plus B4 plus B5, right? I know those are betas, but I'm just going to say B because it's simpler. If you add all of those up, that's going to be 360 degrees. And there's a formal proof for it in your textbook, but just to do a little bit of intuitive reasoning here, if we were to think about walking around the outside of this figure, right, sort of put yourself standing right here. Pretend you don't have a line in your head. If you wanted to head walking this direction, yes, and then make a turn, you'd have to turn B2 degrees right here to then, instead of walking continually on this line, to make a turn and head this direction. Well, same thing here. If you were walking along this side and you wanted to make a turn, you'd have to turn B3 degrees to then walk along this side of the polygon. Same thing here. When you get to this point here, you'd have to turn an angle of B4 to be able to walk along this side, and you'd have to make a turn of an angle B5 to walk along this side, right? And to end up headed in the same direction you were, you'd have to do what? Make a turn of angle B1. Okay, but notice that when you do that, you're now headed in the same direction you started with, right? You made a complete rotation is the idea, and a complete rotation is 360 degrees, right? If you go through all of these turns, B1 through 5, you'll end up heading in the same direction you started out with, right? You're back to where you originally were, a full rotation later. Okay, so let's find the measure of each interior angle of a regular decagon. Remember, a decagon has how many sides? That's 10, right? Deca meaning 10. So we know the sum of the measures of the angles of a decagon is 10 minus 2 times 180. Remember, that's our formula, n minus 2 times 180, right? 180 degrees, right? So that means if we have n is 10, we just plug it in. So the sum of the measures of the angles of a decagon is 1,440 degrees, but it wants each interior angle, right? Which means if this is the total, how do I get measure of a single one? I divide by the number of sides, right? So I take my 1440, divide by 10, and I get 144 degrees. Okay, let's find the number of sides of a regular polygon, each of whose interior angles has a measure of 175 degrees. Okay, so we know that each of the interior angles has a measure of 175 degrees. Well, don't we know, remember, that each interior angle will measure a degree measurement given by this formula, right? Whatever this will be. Don't we know that that's 175 degrees? Yes, that's what we're told. Each interior angle has a measure of 175 degrees. I can then set my formula for the measure of each interior angle to 175 and solve, right? So I have n minus 2 times 180 degrees will be 175 degrees times n. And now I can use the distributive property here to distribute this 180 across the parentheses. 180 degrees times n minus, what's 2 times 180? 360. And that's 175 degrees times n. And now I can just get everything on the one side, right? So let's move this 175n over to 180n by subtracting. So this is 5n minus 360 degrees equals 0. And so 5n equals 360. And so I get n is equal to 360 degrees divided by 5 degrees, and so n is equal to 72. Right? So what that means is that we just found out that the polygon we're working with has 72 sides, which is pretty cool. And I just did it a different way than in the slide, which is okay. All right, last example, and then we'll get out of here. So lines L and K are parallel, and the angles of A and B are shown. Find x, the measure of angle BCA, right? So we want to find this x right here. Well, what we can do is actually say continue this line BC through here. And what we know is that because this BC is a transversal and we know L and K are parallel, that's really important. That means that this 80 right here is actually the same as this angle right here, right? And let me change the color of my pen so you can actually see what we're doing. Red, we'll do red. This angle right here, yes? That angle right there is 80 degrees because of alternate interior angles. Okay, well if that's the case, don't we know then that this is a little triangle right here, and this angle right here, I don't know what that is, but I do know that if I labeled it as question mark or something, right, I would be able to say this angle of 60 plus that angle of 80 here plus what I don't know at that point has to be 180. Yes, because it's a triangle, right? And the interior angles of a triangle add to 180. So that unknown angle there has to be what? 40 degrees, because when I subtract, yes? Which means if this right here is 40 and that angle is supplementary to x, that means that angle plus x has to be 180 degrees. Well, we know what that little question mark is, right? 40 degrees plus x has to be 180, which means that x has to be 140 degrees. What's interesting to note is that x right there is actually equal to what? The sum of this angle and that angle, right? And that's actually will be true, right? In general, because of our symmetries that we've done here, our properties of angles. Okay, thank you for watching video 411.4. Sorry it was kind of long.